So, what if I told you that the sound from a simple guitar pluck holds a fundamental secret about how energy works everywhere? Today, we're going to find the hidden energy that's packed inside a single wave. We'll start right here with a vibrating string, and we're going to end up understanding something about, well, everything from ocean waves to starlight.
I mean, really think about it for a second. You pluck a string, and the sound wave literally travels across the room to your ears. That sound is energy. But where is that energy hiding in that tiny wobbling string? Is it in the string's motion? Is it in its shape? Or is it something else? That's the mystery we're going to solve. So here's how we're going to tackle this. First, we'll look at the two hidden forms of energy. Then we'll build the equations for each one, the energy from motion and the energy from shape. After that, we'll see how they connect, and finally, we'll put it all together into one single elegant formula that just explains everything. Ready? Let's dive in. Okay, so at the heart of our question is a really simple but super powerful idea. The energy in a wave isn't just one thing. Nope, it's actually split into two distinct forms that exist at every single point along that string.
That's right. As the string is vibrating, each tiny little piece of it is moving up and down, right? That gives it energy of motion, or what we call kinetic energy. But at the exact same time, the wave shape is stretching that little segment, storing energy in it, just like a tiny rubber band. So to find the total energy, our mission is pretty simple. We just need to figure out these two parts and then add them up.
Let's start with the one that's a little more obvious, the energy of motion, the wobble, if you will. This is the energy that comes directly from the physical up and down speed of that string.
This part makes total sense, right? A piece of the string that's moving faster has more energy. Easy. The real challenge is, how do we describe that with a precise mathematical formula? Well, physics gives us a classic starting point. Kinetic energy is 1/2 mass times velocity squared. Now, since we're only looking at a tiny piece of the string, we use dk to represent that tiny bit of kinetic energy. Just think of that d as meaning a little slice of.
So how do we adapt this for our string? Well, first up is mass. For a tiny slice of string, which we'll call dx, its mass is its linear density. That's just a fancy way of saying how heavy the string is per inch, we call it mu, times its length. Next, velocity. We only care about its up and down speed. In physics, that rate of change is called dy by dt. So let's just plug those two pieces into our main formula. And there you have it. This is our first building block. This little equation tells us the exact kinetic energy for any tiny segment of the string. It's all about the string's density, its vertical speed squared, and the length of that tiny segment. Okay, part one, done. Now for the second, and maybe less obvious form of energy, potential energy. This has nothing to do with motion. This is all about the shape of the wave. It's the energy of the stretch. The absolute best way to think about this is to picture a rubber band. When it's just sitting there, relaxed, there's no stored energy. But the second you pull it, you're storing potential energy in it. A wave does the exact same thing to a guitar string. It's constantly stretching it from its straight resting position and storing energy as it does. This energy comes from the string's tension. We'll call that T, which is pulling back against the stretch. So the key is figuring out how much it's stretched. And that's just the difference between the curved length of the wave, ds, and its original flat length, dx. Now, without getting totally lost in the mathematical weeds, we can use a little bit of geometry to figure out what that stretch actually is. And it turns out, the amount of stretch is directly related to the square of the slope of the wave at that point, which is dy dx. Bottom line, a steeper wave means a lot more stretch. And so, this gives us our second building block. The potential energy du in a tiny segment is half the tension times the slope squared times the length of the segment. See how different this is from kinetic energy? This one depends on the shape of the string, not its speed. All right, we did it. We have our two pieces of the puzzle, the energy of motion and the energy of shape. And now for the really cool part. Let's see what happens when we put them together. Just look at these side by side for a second. It's really fascinating. The kinetic energy depends on dy dt. That's how the string's position changes over time. But the potential energy depends on dy dx. That's how the string's position changes over space. Time versus space. Two totally different sources of energy coming from the exact same wave. Now, to see how these two energies actually play together, we need a description of the wave itself. We can use this standard function. Don't worry about all the details, just focus on the key parts. A is the amplitude. That's how tall the wave is. Omega is the frequency, how fast it vibrates. And K is related to the wavelength, how long the wave is. These are basically the wave's vital stats. And this is where it gets amazing. When you plug that wave function into our energy equations, you discover something incredible. The energy isn't just sloshing back and forth from motion to stretch. Instead, for a traveling wave, the average energy of motion is always exactly equal to the average energy of stretch. It's a perfect 50-50 split. The two are in perfect harmony. So, this perfect balance means we can now combine everything into one final equation that gives us the total energy carried in one complete cycle of the wave. So, to get the total energy, we just add our two parts together. And since we just learned that they're perfectly equal, the total is simply 2 times the kinetic energy, or 2 times the potential energy. It's really that simple. And so, after all that, we arrive at our final destination. This beautiful equation tells us the total energy that's packed into one single wavelength. It's all about the string's density, its amplitude squared, its frequency squared, and the wavelength itself. This is it. This is the hidden energy of a wave, all laid out. So what does this equation actually tell us? Well, look at those squared terms. That's the secret sauce. If you double a wave's amplitude, make it twice as tall, you don't get twice the energy. Oh no, you get 4 times the energy. Same thing goes for frequency. This is exactly why a high-pitched scream carries so much more piercing energy than a low hum. Even if they're at the same volume, the energy just explodes with height and speed. So, when it all comes down to it, the crucial point is this. While things like the string's thickness and the wavelength definitely matter, the real drivers of a wave's energy are its amplitude and its frequency, how big it is and how fast it wiggles. That is where the power truly lies. And that brings us to this final powerful idea. We started with a simple guitar string, but the secret we uncovered, that a wave's energy is locked to the square of its amplitude and frequency, that applies to nearly every wave in the universe. So the next time you see a ripple in a pond or feel the warmth of the sun on your skin, you'll understand the hidden physics of the energy it's carrying, right across space and time.